Welcome back, everybody. Before we start the next talk, Stephanie has a quick announcement.
Yeah, so you can probably guess what this is about. Please fill in the survey. There were already 134 people who filled in the survey yesterday, but curiously, very few students and postdocs have filled in the survey. So, I mean, we want to know your opinion. Please fill it in. And also, I would like to remind you that I'm going to close the survey about 3 hours before the business meeting. So you should fill it in before lunchtime tomorrow, basically, because I need some time to make some nice pictures and stuff. So please go to the website. Thank you.
Okay, I'm very pleased to introduce our next speaker, who's Marco Piani from Waterloo and also Strathclyde, who's going to be telling us about EPR steering and subchannel discrimination.
Okay, thank you. Good morning, everyone. Can you hear me? Yeah? Okay. So I would like to start by thanking the organizers and the program committee for giving me the opportunity to tell you about joint work with John Watrous, who is the University of Waterloo. So today I'm going to try to convince you that all entangled states are special, but some states are more special than others. Okay, so how are we doing that? Well, and why? So, well, we have two goals, if you want, in mind, and those are that of understanding quantum correlations and facilitating their exploitation. And we are going to do that in a particular way, specific way, that is through an operational characterization that deals with the discrimination of physical processes. So we want to prove that they are useful, these correlations are useful in this discrimination. So there are many black boxes in quantum information processing. For this talk, I will stick instead to mystery boxes. So these will represent a physical process or a transformation. And the idea is that you have an initial state and that gets transformed with potential, well, very different final states. So let me be more precise. What we are going to consider is one channel that has subchannels. So in particular, this notion is known as quantum instrument. So what you have here are completely positive maps that are not necessarily trace preserving, but they sum up to a quantum channel, so a trace preserving map. And we think of these as branches of the evolution. So this scenario includes the standard channel discrimination, where these subchannels are actually proportional themselves to channels, so with some weight, a probability. For example, in the standard channel discrimination problem, where you have just two channels, you would have a total channel that is just the sum with equal weight of two channels, lambda 0 and lambda 1, to be discriminated. But the scenario that we are considering is more general, right? So, for example, you could think of the branches of the amplitude damping channel. So you may know that we have seen that these actually during the tutorials during the last weekend. So you have just two Krauss operators for the amplitude damping channel, and each Krauss operator, you may think of that as constituting a branch or a subchannel of the evolution. So what is the task? Is that of minimum error subchannel discrimination. Okay, so you have this transformation. Again, it's an instrument. We have fixed some decomposition into subchannels, and we want to decide which subchannel takes place. Again, let me be more precise. We have an initial state, so some density matrix, that is fed to the evolution, to the channel, and that is made of these subchannels. In principle, the information about which subchannel takes place is available to some party, but we have only access to the quantum output of this channel. And what we want to do is to guess what was the transformation based just on the quantum output. So what we are going to do is to perform a measurement described by a POVM with a classical output itself, B. And now this defines a joint probability distribution for the two labels for which transformation took place and what is our guess, just like this. And what we want to do is to optimize the probability of guessing correctly. So we are going to consider something like this, where we are guessing correctly if B is equal to A. Okay, so this probability of being correct obviously depends on the initial input, on the instrument that we are considering, so this set of subchannels, and our choice of measurement at the output. So if you now maximize over the measurement, you can define a probability of being correct that depends only on the state and on the subchannels. And finally, you can optimize also on the input, arriving at an expression that just depends on your subchannels. And here I indicate no entanglement in the sense that we are not making use of entanglement yet. Indeed, we could try to guess these subchannels, which subchannel took place, with a more general strategy that involves correlations. So we have this, the probe, also known as Bob or Mario, and we are going to introduce an ancilla, okay, Luigi if you want, and we are going to consider them entangled, so they are good brothers. So what do I mean by entangled? Just to remind you, we mean entanglement is defined by negation. So the joint state here in general is not going to be, it will not be possible to write it as the convex combination of product states for the probe and the ancilla. In this case, if this decomposition instead applies, well, we say that the state is separable or unentangled. Doesn't mean that it doesn't contain correlations, but those correlations are just purely classical due to this classical label lambda. So this is the scenario now. Okay, we are feeding the probe to the mystery box, and then we perform, in principle, a global measurement of both the output probe and the ancilla. And you can think of this as a bigger channel where the ancilla, though, doesn't evolve. Okay, so we can define now a probability of being correct that makes use of entanglement, just taking the previously defined non-entanglement probability of success and just considering a different class of channels where we have that the ancilla doesn't really evolve. Okay, so, and this is the best probability of success allowed by quantum mechanics. So it's well known, so I would not be talking about this if it was not the case that when you use entanglement, you can perform better than without entanglement. This is something well known in the quantum information community and even before to mathematicians. And let me mention that we need entanglement. So we would not have this, we would not be able to perform better if we were using the classical correlations of a separable state. That's very important. So in 2009, we proved a slightly different result that is tailored to a specific entangled state. So give me an entangled state, however weakly entangled you want or you can create it. So then I can choose, so there are some subchannels. In this case, actually, we were able to work in the standard scenario of 2 channels. We can find, or in principle, construct these channels so that are better discriminated by using that entangled input. It means that we perform better than without entanglement, even if here we are allowed to choose the best possible input, right? So just without correlations. So with this, well, we like to think of it as the fact that every entangled state is useful for subchannel discrimination. Okay, so you have to find which instance of the task. Okay, so I'm gonna use here the word resource in a vague way, probably, but we think of this now as a resource. So it allows us to perform better. If we were not able to create entanglement here, we would be doing worse. But it's probably not the only resource. So we have a giant global measurement there that might be expensive. I mean, if you're an experimentalist, really expensive, concretely. So what we want also conceptually is to promote this to the only non-local resource. So what we are going to consider is something that we introduced already with Matthews in 2010, that is, we restrict the final measurements to be performed via local operations and classical communication. Okay? So, and the question now is, does every entangled state stay useful in this scenario, where you impose, so if we don't impose constraints on the final measurement, yes, every entangled state is useful. You impose constraints, what happens to this feature? Well, you may know that working with the general LLOCC class is tough. And what we do, we change the problem in a sense. So we consider the case where communication can go only in one direction. And one can argue that this is the only interesting direction. So working with communication that goes from the ancilla to the output probe is not interesting. So we're going to be dealing with this scenario where we use one-way, so-called one-way LOCC, as to perform the measurement. So what are our main results? Well, if measurements are restricted to one-way LOCC, then only steerable states can remain useful. You lose the fact that every entangled state is useful, must be steerable. If measurements are restricted to one-way LOCC, all steerable states do remain useful. Okay, so you have a characterization. Before we had this characterization, if you want, of entanglement versus separable, and what with global measurements. And what we have now here is that if we restrict the class of measurements, we actually characterize steering. And we can do more in the sense that we prove that the usefulness of the probe ancilla state, the entanglement there, when you consider one-way LOCC as measurements, actually quantifies its steerability. And you may wonder what steerable is at this point. Okay? So let me recall the notion of steering. So steering was probably first encountered by Einstein-Podolsky-Rosen in their seminal paper, and was, but the name was introduced just later by Schrödinger. Steering deals with the fact that, in principle, Alice can control the conditional states of Bob through local measurements on her side. So, of course, she doesn't control this state of Bob because that would imply faster than light signaling, not possible. But still, she can do something about conditional states. Conditional on what? Well, the idea is that there are several measurements she can choose among, and these are labeled by label X. So this is the choice of measurement. Every measurement has an outcome A, and we define this conditional state of Bob. Notice that this state is not normalized to 1, the trace, but is normalized to the probability of the outcome for the measurement. So as an example of steering, let me consider a shared singlet, so this anti-symmetric state. You may know that is perfectly anti-correlated. So let us say that one possible measurement of Alice is the measurement in the computational basis. Well, this induces an ensemble decomposition for the reduced state of Bob, that is the maximally mixed state, that is composed by the states in the standard basis, 0 and 1. And notice that I have included there the probability 1/2, that is the probability of the outcome of the measurement. But she could choose a different measurement, so for example in the plus-minus basis, and again, because it's the singlet, perfectly anti-correlated, you would obtain an ensemble like this. So these are two valid ensembles for the reduced state of Bob, and they are generated by a different choice of the measurement of Alice. What we do is to focus on collections of these ensembles. The following Matthew Pussy we call an assemblage. Right? And notice that this assemblage doesn't contain information about the exact measurements performed by Alice, but only about the relation between the choices of measurement of Alice and the outcome of Alice. Okay? So in that sense, we are going to discuss how this is related to entanglement, and we are going to see that steering then allows for the verification of entanglement in a semi-device independent way, because we don't need to know the exact details of the measurement of Alice. So, and the question now is steering really quantum? Why is it? So by this I mean, are we seeing the spooky action at a distance that is due to entanglement? And this relates to the fact of whether we can or cannot think about Bob, or this particle of Bob, being in some pre-existing, potentially local hidden state. So what do I mean by that? Well, let us say that what we want is to think to consider a local hidden state model. So there would be some ensemble decomposition, let's say a particular one, with hidden states and a probability distribution over these hidden states. And this lambda is the label of the hidden state. And now we ask whether these conditional states on Bob that are generated by the measurements of Alice, whether there exists such choice for the hidden states and a choice of conditional probability distributions so that this is valid, this relation is valid. Well, in that case, we say that this assemblage is unsteerable, and we don't have a spooky action at a distance, because actually it means that the measurement of Alice corresponds just to some processing of classical information. It's not a quantum effect. And here, at this point, I want to mention that we can, if this is valid, then we can always shuffle things around, massage things, so that these conditional probability distributions here that depend on these, let's say, classical hidden variable, well, are actually deterministic. So for a given x, so fixed lambda, to every x, you have a fixed associated a. So again, we define steerable in the negative. So we say that an assemblage is steerable if it is not unsteerable. And we say that a bipartite state is steerable if it can generate steerable assemblages with the proper choice of measurements. Okay? Otherwise, we say if there is no such a choice of measurements, then the state itself is unsteerable. So it's easy to see that all unentangled states or separable states are unsteerable. And moreover, if you find through the procedure that we described that your assemblage is unsteerable, you can always imagine that it was generated through sharing a separable state. So steering, if you see steering, the fact that the assemblage doesn't allow to be described through these local hidden states, then you know that there was entanglement. But one novelty is that also some entangled states are unsteerable. Okay? So steering is a stronger form of entanglement. It's just not enough to be entangled to be steerable. So normally, one possible classification of bipartite correlation of bipartite states divides them in unentangled and entangled. And then you can start to have a finer classification. Right? So for example, you can describe local states. There will be states, for example, there are states that are entangled because they are not unentangled, but still you cannot violate Bell inequalities with those. Right? Famous examples are Werner states in the proper range of parameters. And the consideration of steering makes this classification finer. So you would have here states that are unsteerable by Alice, and you can imagine, because it's one part in measuring, that steering is a directional property. So you would have states that are unsteerable by Bob, and they don't necessarily coincide. Right? So you have some rich structure. And so what we did in the past then was, with the previous work with John Watrous, was to characterize this border, where this work is about characterizing this border. Okay? So let me go back then to the scenario where we have subchannel discrimination with one-way LOCC measurements. One-way LOCC measurement works like this. There is a choice of measurements on the output probe. The result is communicated on the side of the ancilla, and there is the choice of one among many possible measurements. And the output, now the outcome of this final measurement, is our guess for which subchannel took place. So this defines the class of one-way POVMs, one-way LOCC POVMs. And we can cast our question is, for given an entangled state, is it that it provides an advantage so that the probability of being correct with these one-way measurements is larger than the case where we don't use any entanglement, but we are free to choose the best possible input. Okay, and the relation with steering, you should already see it in a sense, is due to the fact that here we choose many possible measurements on the ancilla. Okay, so this is the same kind of measurement that we use in steering. And one realizes pretty quickly that in order to have this relation, so that you perform better, these measurements must create a steerable assemblage. The reason is that otherwise, well, a separable state would have performed as well. So this is the intuitive reason. So, and no better than without correlations. So steering is necessary. Only steerable states can be useful under the one-way LOCC assumption for measurements. And so that means that also now some entangled states become useless, sorry. So, and what we do is, that is probably more surprising, is that all steerable states do stay useful, okay? So how do we do that? Well, if the state is steerable, consider any choice of measurements that, well, reveal the steerability. This generates a steerable assemblage. And what we do is we introduce a quantifier for how steerable that assemblage is that we call the robustness of steering. So I don't want to go through the definition here, although it's simple, but I say graphically. Now, if you think of the space of assemblages, you have an assemblage here, and there is a subset, a convex subset of unsteerable assemblages that are compatible with unentangled states. And what we do is we consider the injection of noise, if you want, through the mixing with an arbitrary assemblage, so that we bring in this assemblage that in principle was steerable within the set of unsteerable assemblages. And we check this parameter, and we want to find what's the minimum amount of noise that we need to add, being free to choose whatever other assemblage here to mix with. So having defined the steering robustness for the assemblages, we can define it for entangled states themselves. Simply, we optimize overall assemblages that can be generated using that particular bipartite state. And now our results can be cast in terms of this quantifier. So consider this ratio, right? So we have here then an instrument, so a collection of subchannels. We consider the probability of being correct in determining which subchannel takes place using this input state rho AB. And we consider the ratio of that with the best that we can do without using correlations. And now we optimize overall possible subchannel discrimination problems. Well, what we do is to prove that this is essentially equal to this steering robustness. So this is our main result that tells you that every steerable state, so that has non-zero steering robustness, is useful. Plus, well, you see that its ability to improve our, let's say, guessing probability is exactly related to the steerability. So just briefly, what are, thanks. Well, the proof is, well, one direction is very simple, essentially, is due to the definitions. And the other, the upper bound, the fact that the upper bound can be reached is proved by constructing suitable subchannel discrimination problems. So the main observation is that finding this robustness for the assemblage corresponds to the solution of a semi-definite program. So here is written, you don't need to check the details, but so there are these three variables, these f's, and that satisfy some constraints. They are positive, and they satisfy a constraint that is related to the deterministic strategy. Because you can imagine at the end, we want to see that the non-steerable assemblages cannot perform too well. Okay, so it's a bound on that. And another way of looking at it is if you're familiar with entangling witnesses, is well, we use entangling witnesses that is Hermitian operators that can tell apart separable from entangled states based on their expectation value. That if you want is a kind of inner Hilbert-Schmidt inner product between the state and this entangling witness. Well, these F's are just some steering witnesses. Okay, so you have also an inner product in the space of the assemblages, and they discriminate whether you are, if you want, on one side, so you are unsteerable or not in this sense. They constitute an hyperplane in this space. So the point is that using the information provided by the SDP, by using the existence of these F's with these particular properties, well, we build this subchannel discrimination problem. Particularly, we choose the subchannels to be quantum to classical. So these correspond to some kind of measurement. Remember, the F's are positive semi-definite. And the fact that the output here is classical helps us to know what is the optimal measurement on the output probe, right? So because you are classical, you better measure in that basis. And we take care, so we use some normalization factor there to make sure that these can be completed to a channel. These subchannels can be completed to a channel, and we take care of that, of completing them to a channel, by introducing some dummy subchannels. So with this construction, overall we achieve something like this, that for the constructed tasks, we have some relation like this. And at the end, without going to details, we proved that the upper bound was achieved. So a remark, our SDP approach was based on, was also inspired by previous work by Skripchik, Navasquez, and Cavalcanti. So conclusions, I hope I have convinced you that all entangled states are special. For example, they provide an advantage in channel discrimination, but some are more special than others, so that even if you introduce constraints on what you can do at the measurement, well, steerable states stay useful. So we have introduced also this robustness of steering. I can tell you more about the properties. So it's good because it has operational interpretations like resistance to noise, but also the advantage in a precise task. And some open questions. Actually, we don't know how to compute that, even in very special cases. So some project, if you want, for students. And then, of course, we introduced the task of subchannel discrimination. It would be interesting to know whether we can still see the advantage of steering in proper standard channel discrimination. And we have, remember, you have tweaked the problem, and we have only considered one way LOCC. Can we say something about the LOCC scenario? And finally, well, we characterize entanglement via channel discrimination. Now we have characterized steering. Can we characterize also non-locality with similar problems? Thanks a lot.
Do we have any questions? Yes, Debbie.
So I wonder whether the direction of that one piece of communication actually matter, because the channel actually on one side.
Yeah.
And so it looks like there is some asymmetry, whether the message goes from the reference to the output versus the other way around. Have you thought about that?
Yeah, there is such an asymmetry. So I mentioned that, well, you want to, even in the standard use of correlations to discriminate channels, the channel acts on just one part of the entangled state, right? So that's standard. And now I said, yeah, it's important whether the communication goes from the probe to the ancilla or from the ancilla to the probe. The other direction, if you consider only one way, you can argue that is not useful. So considering in that direction is not so interesting.
We have time for another question. Okay, I have a question, sort of on sort of what is the meaning of subchannel discrimination? So you say you discriminated. I think the language you used, you said you discriminated which subchannel happened.
Yeah.
But if the subchannel's not a channel, how can it happen?
Okay, so it happens in the sense that you can imagine the channel definitely happens, right? Yes. So now you can still imagine that there is a leakage or whatever of the information about which subchannel takes place. That is actually, that information is accessible to someone. And now I'm saying, can we obtain the same information looking at the quantum output?
One more question over there. Was that a question or not? Yes.
So maybe two questions. One is there anything known about the complexity of determining if a state is steerable or not? Like, you know, for the separable case, it's empty hard.
I would imagine is you can run. It's even tougher, and because you have to also to go through the measurements. It's like with when you have to determine whether a state is non-local or local. First of all, you have to go and choose the right measurements to reveal that non-locality. So I don't know how you would go necessarily about that, but once you have performed the measurement, checking whether the assemblage that you get is steerable or not can be done with the SDP. So in a sense, efficiently. Although of course the number of strategies grows exponentially. So deterministic strategies. So it's still tough.
And do you know if the you can also write the robustness of entanglement as an SDP?
Yes, you can. Yeah.
Oh, I see. Okay.
Okay, let's thank Marco again.
Thank you.